with the development of various experiments and its explanation by Planck's quantum theory, it is now conclusively proved that light is sometimes playing as wave and sometimes also it is playing as the particle. Photoelectric effect, Compton effect and the black body radiations, all this that conclusively proves this light is having the particle nature. But the wave nature and particle nature, both these two are contradictory. Wave spread space and coming from the disturbance, and it is highly delocalized. But in case of the particles, it could not be found in two places at the same time, and it is highly localized. So the particle aspect in case of light, particle aspect you can say photoelectric effect. While the wave aspect, diffraction of one example, the diffraction of X-rays. Diffraction of X-rays. Wave nature means it will go in this fashion, coming from this disturbance, and it is like that, occupy some space, and it is the particle nature means it occupies this one place. These two contradictory aspects actually inherent in Planck's quantum theory. According to Planck's quantum theory, the energy packet or the particle, which is called photon of these radiations, having this energy epsilon photon equal to hc by lambda. Lambda is the wave aspect, whereas the particle is having where the energy of the photon is the particle aspect. So both this particle aspect and this wave aspect of this Planck's quantum theory is inherent. First, de Broglie, in 1924, French scientist derived or actually formulated in a form of hypothesis the relationship between the particle aspect and the wave aspect of these electromagnetic radiations. He used this Planck's concept, epsilon photon equal to hc by lambda, and also the Einstein's theory of relativity. If the photon is having the mass m and its m is annihilated into energy, then energy of the photon will be coming up, and this energy of the photon will be equal to mc. C is the velocity of light in vacuum. So equating these two, we have the hc by lambda equal to mc squared. 1c we can cancel, and this lambda equal to h by mc. mc is the momentum of this photon, and so we can write this lambda equal to h by p the momentum of this photon. So far we knew that this light is having this wave nature, and different experiments have been nicely explained in terms of this wave nature. But now it is coming to show the particle nature. So automatically one question will arise, how then, but so-called we know the particles, they must also have this wave nature. As we know, the nature always prefers this symmetry. Then particle like this electron, whenever electron is moving, it is also associated with this wave. And this for electron, and this lambda equal to h by p, this equation is still valid for this electron or any subatomic particle in motion. And this lambda we call this matter wave, and this is the momentum of this particle. So suppose this electron, these two natures are reciprocally related. In some experiment, if this momentum is prominent, then wave aspect remains subdued. But it is the fact that whenever a dynamic particle always is associated with this wave, both these two are complementary. But one aspect when appears, one aspect when revealed, then another aspect remains concealed. Means these two are mutually exclusive, but they are complementary. Always associated. Dynamic particle is always associated with this wave. But whenever we consider this electron, this velocity is very high, mass is very small, and so lambda equal to h by mv, and h equal to 6.626 into 10 to the power minus 34 joule second, whereas m 9.1 into 10 to the power minus 31 kg, and velocity. Suppose we are considering the orbital motion, both orbital motions of this electron, then it is about 2 into 10 to the power 6 meter per second, and this comes to 3.64 angstrom. So this range of this wavelength could be determined by means of experiment, as we have seen in case of the electron diffraction experiment made by Davison and Jarma in the year of 1927. But whenever the cricket ball is running, cricket ball is moving, cricket ball is thrown, it's say cricket ball, for this cricket ball, m is 0.156 kg around, and velocity is suppose 60 kilometer per hour, and in that case lambda is found to be very, very small, and it is equal to 2.65 into 10 to the power minus 24 angstrom, which is very, very small, and no experiment, no instrument can determine this wavelength of such low value. And this is why this cricket ball is not moving in this wavy fashion. It moves in a straight line. It moves in a straight line, while it will move in a form of waves. First, Broglie, Davison and Jarma in his electron diffraction experiment actually proved this electron is having this wave nature, and the wavelength of this electron is also determined by them. Electron electron deflection experiment. Electron deflection experiment. It is a very nice experiment. In 1927, Davison Jarman actually did this experiment and find this wavelength of this electron rays. This is the nickel crystal, and nickel crystal, it's a nickel crystal acting as the deflection grating, and the monoenergetic means all the electrons, means all these electron rays are having the same energy. Monoenergetic electron rays falls on these nickel crystals having the atoms in a fixed distance arranged symmetrically, and whenever this incident electron rays falls on this nickel atom, it is reflected in this way. Another incident electron ray also reflected in this fashion, and these two reflected rays will form constructive interference when the path difference between the two diffracted rays becomes equal to integral multiple of lambda, and path difference is AC. And the AC is the path difference of these two diffracted electron rays, and this path difference must be equal to n lambda to make these two diffracted electron rays form the constructive interference. For the case of the AB, the distance between the two successive nickel atom is equal to AB and 2.15 angstrom, and this is called T. So this AB is equal to D into cos 90 minus theta, and this is equal to D sin theta. So this n lambda becomes equal to D sin theta. This is the formula of this electron deflection experiment made by Davison and Jarman according to the same principles of this black X-ray diffraction. Experimental setup for this Davison and Jarman like that. This is the heated tungsten acting as this electron gun. Electron is passing through this slit, and they are accelerated by a potential V, and they are falling on the rays are falling on this nickel crystal and diffracted. Here is electron collector. Say one galvanometer can be set here within this scale. So when this diffracted rays will form the constructive interference, this galvanometer will record the current which is having the maximum value. Means the diffracted electron rays having the maximum intensity at this theta. Theta is the angle between the incident ray and the diffracted rays. This is the theta. So by the use of, and here the V is potential applied for this electron to accelerate, to give this kinetic energy, and the energy is given EV, the energy given to this electron, and these electrons will have this kinetic energy half mv square. Since V is constant and E automatically constant, is the charge of this electron, so the electrons passing through these plates will have monoenergetic value or having the same kinetic energy. Or you can write this P square divided by twice M. twice m. So the now we calculate the de Broglie predicted value of lambda from de Broglie relation. De Broglie relation. De Broglie relation. This lambda lambda is equal to h by p, and this is p. This is the p. This is ev. This is 2m, and so this lambda will be equal to h divided by root over of twice m e v. By this way, we can calculate the wavelength of this electrons as predicted by this de Broglie relations. Putting all the values, say h equal to 6.626 into 10 to the power minus 34 joules second, and divided by root over of 2 into mass of this electron 9.1 into 10 to the power minus 31 kg, and this charge of this electron is 1.6 into 10 to the power minus 19 coulomb, and potential, when the potential is applied, the 54 volt, this theta found to be 50 degree by this Davison-Jarmar. Means at this 50 degree angle, the diffracted rays forms a constructive interference. So it is 54 volt, and this lambda is found to be 1.677 angstrom. 67. Another and the value of lambda experimentally determined by the Davison-Jarmar by the use of this formula, we can have this for n equal to what? First order diffraction, and so lambda equal to d sin theta. D is the distance between the two atoms of this nickel crystals, and it is 2.15 angstrom, and theta sin theta, and theta equal to 50 degree, and these two will give you this lambda 1.65 angstrom. So it is very nicely it is seen the Davison-Jarmar experimental value of this lambda associated with this electron is matching very good with this predicted value of this de Broglie relation 1.67 angstrom. This conclusively proves the electron is having wave nature also. And now we come to the application of the de Broglie relations. Applications of this de Broglie relations. Application of de Broglie relation. De Broglie relation. I shall cite here two applications. So one is Bohr hydrogen atom. In case of Bohr hydrogen atom, this electron is rotating in a circular orbit, keeping this nucleus at its center, and this is the stationary state. Means this whenever so long this orbit electron will move in this orbit, the energy of this energy remains fixed, remains stationary, constant. So this, whenever this electron is moving, that is as wave associated with this electron, and these waves, whenever it is moving in a stationary state, the wave also forms the standing wave. Standing wave means the maximum and minimum will not change. Position of the maximum minimum will not change with the time, and this we can write in this way. So this maximum minimum is be fixed in its input, does not change with the time. So if we consider this standing waves, then the circumference of this orbit, circumference of this orbit must be equal to the integral multiple of lambda. Or by putting this value of lambda according to this de Broglie relations, lambda equal to h by p or h by mv. So this n into h by mv we can write by using this de Broglie relations, or mvr equal to n into h by twice pi, and this is a very important postulate of this board, and by the angular momentum, this is called angular momentum, and this angular momentum equal to n h by twice pi. Angular momentum is quantized. By the use of this quantized value of this angular momentum, it is possible to determine the energy of this electron in this orbit, and we have to use another relations, centrifugal force equal to this centripetal force, and by the use of these two relations it is easy to calculate the energy of this hydrogen atom, and it is equal to 1 by n square into 2 minus 2 pi square m e to the power 4 or divided by h square. So energy will have discrete values, n equal to 1, 2, 3, 4, any positive integer, etc. Another application I can cite the particle in one-dimensional box. Particle in 1D box. And here is a box, x 0 to L, the length of this box, and here potential energy equal to 0 within this box, and outside this potential energy equal to infinity. Here P potential energy infinity. So here the electrons, here the any particle, subatomic particle, is moving to and fro motions within this box along this x-axis. And suppose this is the L, and for the when the particle is moving to and fro motions, wave is also associated with these motions, and these waves, whenever it is the minimum n equal to 1, this wave will be like this, and for the second n equal to 2, it will be like this, and whenever this n equal to 3, then wave will be equal to like this. That means the length of this box must be equal to the integral multiple of lambda by 2, or a twice L equal to 10 lambda. So again, now we can put the value of lambda from this de Broglie relations. So this will be equal to n into h by p. So p equal to this linear momentum of this particle in one-dimensional box becomes equal to n into h by twice L, and this is quantized. So by the use of quantized, and this quantized value of this linear momentum, this particle, we can calculate this energy value, and this energy of this particle in one dimensional box equal to kinetic energy plus potential energy, but potential energy equal to 0, so it is only the kinetic energy, and this is equal to p square divided by 2 If we put this p equal to this value, then energy equal to n square divided by h square divided by 8 n square into h square divided by 8 m l square. So it is de Broglie relations is very successful to determine the quantized energy values of this particle in one dimensional box. This is like that, and also we can calculate the energy value of this more hydrogen atom by the use of this de Broglie relations. So this de Broglie relations finds so much applications, and Einstein himself appreciated the de Broglie hypothesis in a number of ways, and this is all about the de Broglie relations. Thanks to you all who are watching this video, and I hope it will be helpful. It may be helpful to the honors students, and if they find any use, kindly make a comment to my video lecture.